Hi everyone, I am Beyza and welcome to our project presentation. Our project name is Bioshield, a biodegradable titanium-based filter cartridge designed to capture microplastics fibers directly from household laundry wastewater. Here is our course outline, and I will begin by introducing the problem and our outline. I will start with the introduction part. Every time we wash a synthetic clothing, polyester, nylon, acrylic, we release hundreds of thousands of microplastic fibers into the water. In fact, a single laundry cycle can release more than 8,000 microplastic particles. Once released, these particles are extremely persistent. In solid environment, microplastics can remain for over 100 years because they are hydrophobic. They do not simply dissolve in the water, and even when wastewater does reach a treatment plant, approximately 35% of the microplastics still escape into the river, lakes, and oceans. This is not just an environmental issue, it's a human health issue also. Microplastics have already been detected in human blood, in lung tissue, and in reproductive organs, and even in brain tissues. Studies suggest that microplastics accumulation may negatively affect the cell motility and reproductive health also. While research are ongoing, the early findings are alarming. Now my colleague Pelin will explain why the current solutions are falling short and now how Bioshield fills the gap.
Thank you, Beyza. I'm Pelin and I will continue with the presentation. As my friend Beyza outlined, the scale of this problem is significant, but current solutions are simply not good enough. On the left side of the slide, you can see the core limitations of what is currently available. Mechanical-only filters have low efficiency for very fine fibers. Many particles can pass right through. Even worse, most of these filters are themselves made from non-biodegradable plastics, which means that when you throw them away, you are creating more plastic waste to solve a plastic problem. Maintenance is also a barrier. Filters that require frequent manual cleaning simply don't get used consistently. At the municipal level, wastewater treatment plants were not designed with microplastic capture in mind. Upgrading them would require enormous investment that would take years and billions in funding. On the right side, we see what an ideal solution looks like. It should capture microplastics at the source, meaning the washing machine itself, before the water ever reaches the sewer. It should be made from biodegradable materials so it creates no secondary waste, and it should be easy for any household to use without any changes to existing equipment. This is exactly what Bioshield is designed to be. Bioshield is a plug-and-play filter cartridge that connects to the drain system of a standard washing machine. At its core is a porous chitosan foam, chitosan being a natural biopolymer derived from crustacean shell waste like shrimp and crab. This foam is chemically modified with amine functional groups, which give the material a positive surface charge. Why does that matter? Because most microplastic fibers carry a negative charge. So when water flows through the cartridge, the microplastics are electrostatically attracted to the foam and absorbed onto its surface, in addition to being physically captured in the pores. This dual mechanism gives Bioshield a significant efficiency advantage over mechanical-only filters. And crucially, both the foam and the outer casing of the cartridge are made from biodegradable biopolymers. When the cartridge reaches the end of its life, it can be composted. No secondary plastic waste at all. Now my French Freda will continue.
Thank you, Pelin. Our main goal is clear: to develop a biodegradable, amine-functionless keratosan filter cartridge capable of removing 85 to 95% of microplastic fibers from household laundry. Find 5 quantitative key performance indicators to make this goal concrete and measurable. First, a microplastic removal rate of at least 85 to 95%. This is our primary performance target, measured by comparing particle concentrations before and after filtration. Second, a bed surface area of at least 2,000 square meters per gram for the chitosan form. Surface area is directly related to adsorption capacity. The larger the area, the microplastics the material can capture. Third, a pressure drop of less than 10% across the filter. This is essential for compatibility. If our filter slows down the washing machine's drainage, users will remove it. We target less than 5% in practice. Fourth, a durability of at least 30 washing cycles before the cartridge needs replacement. And fifth, 90% mass loss of chitosan, medium with 6 to 12 months under composting conditions with no harm residues. Our project is structured across 30 months, 36 months, and 8 objectives organized into 3 phases. In phase 1, the foundation phase, we conduct a comprehensive literature review and begin the synthesis of Paris's chitosan form. This takes us through the first 10 months. In phase 2, development, we move into amine functionalization, material characterization using TEM and BET analysis and FTIR spectroscopy, and begin filtration performance testing. This is the core scientific phase and extends from around month 8 and month 28. In phase 3, validation, we evaluate stability and biodegradability through repeated cycle testings and soil composting trials. We then integrate the optimized material into the final plug-and-play prototype and validate under real washing machine conditions and prepare the final report. The phases overlap intentionally. This reflects real engineering practice. We don't wait for one test to fully complete before beginning the text. Now, Alena will walk us through the detailed tech methodology, how we actually synthesize and build the filter.
Thank you, Shweta, and I will continue with how we actually make the filter material. The synthesis process has 4 steps. In step 1, we dissolve 1.5 grams of ketosine in an acetic acid solution to produce a stable polymeric acid. In step 2, we introduce N-octane as the oil phase and SPAN-80 as an emulsifier to create an oil in water emulsion. The oil droplets act as sacrificial templates. They define the pore structure of the final material. In step 3, this emulsion undergoes freeze drying, also called eophilization, which removes the liquid phases and leaves behind an interconnected 3-dimensional porous network. This is the ketosine aerogel, which has a very high surface area, enabling efficient microplastic retention. In step 4, we apply a biomimetic coating called DAPEI, dopamine and polyethylenamine, through co-deposition. This introduces abundant amine groups onto the foam surface. These amine groups carry a positive charge, which is the key to the electrostatic capture mechanism. This approach was directly inspired by the work of Young et al., published in 2024, who used a very similar functionalization strategy for carbon dioxide structure. The result is a foam that captures microplastics both physically through its porous structure and chemically through electrostatic attraction. Okay, now let's look at how this material is assembled into a usable product. The ketosine foam is housed inside a biodegradable outer casing produced by 3D printing using biopolymers, which connects directly to the washing machine drain outlet like any standard plumbing adapter. The cartridge uses a dual-layer filtration approach. The first layer is physical. As wastewater flows through the porous foam, larger fibers are mechanically trapped in the pores. The second layer is chemical. The positively charged amine groups absorb smaller, negatively charged microplastic fibers that pass through the first layer. The interconnected pore structure is also designed to ensure minimal flow resistance. Our target is less than 5% reduction in drainage flow rate, meaning the washing machine operates exactly as normal. When cartridge is saturated, the user simply removes it and replaces it. No tools, no plumber. And since both the foam and the casing are biodegradable, this spent cartridge can be composted directly. We will source kerosene from partnerships with local seafood processing companies, making use of crustacean shell waste that would otherwise be discarded. A true circular economy solution. And now Sarah will present our expected outcomes and the resources behind this project. Thank you.
Hello, my name is Hatice Sarayurtlu, and I'm going to talk about the goals and performance targets. Uh, so, what do we expect Bioshield to actually achieve? The bar chart on the left compares microplastic removal efficiency across three scenarios. A conventional mechanical washing machine filter achieves a roughly 40% removal. Typical wastewater treatment plants bring that up to around 65%. Bioshield targets 90% removal, a significant improvement at the point of the generation before any municipal treatment is even involved. On the right, we have three outcome categories for water quality up to 19% fewer microplastic fiber entering aquatic ecosystem from a household equipped via Bioshield. For environmental impact, zero secondary plastic waste because the entire cartridge decomposes within 6 to 12 months under composting conditions, leaving no harmful residues. And for user compatibility, the cartridge swap takes under a minute, requires no tools, and fits existing washing machine during ports without modification. Yes, and this is our project roadmap. To bring Bioshelf from concept to prototype, we have proposing a total research budget of the 1 million US dollars, deploying over 36 months. The largest portion of the budget are allocated to personnel, approximately 25%, and to raw materials and chemicals, another 24%. Key materials include high purity keratosan, citric acid, as a green crosslinker, and the DAPAI functionalization agents, laboratory equipments, specifically for cement bed instruments, are already available at Walsh University's Chemical Engineering Department, which significantly reduces capital expenditure. For the bio for what? For the biodegradable outer casting, we plan to partner with a biopolymer manufacturing company that specializes in 3D printed, which allows our team to focus on the core chemistry and filtration science. For for raw material sourcing, we'll establish partnership with local seafood processing companies to obtain cross-ocean shell waste, the raw material for keratosan, at low cost while also solving a disposal problem for those companies. Thank you.
Hello everyone, my name is Dolunay Hızlı and I will be presenting the conclusion of our Bioshield project. To close, let me summarize why we believe Bioshield represents a genuinely new and meaningful contribution to addressing microplastic pollution. First, Bioshield captures microplastics at the source, at the washing machine, before they ever enter the sewage system. This is fundamentally more efficient than trying to remove them downstream. Second, every component of Bioshield is biodegradable. The chitosan foam decomposes in soil within months. The biopolymer chasing follows the same path. There is no trade-off here. We are solving a plastic problem without creating more plastic waste. Third, the design is plug and play. It requires no modification to existing washing machines. no installation cost, and no technical expertise from the user. This is critical for real-world adoption. Fourth, BioShield is grounded in established science. The amine functionalization approach is directly drawn from peer-reviewed research by Zhang et al. 2024, and the electrostatic adsorption mechanism is well understood in materials chemistry. Fifth, the concept scales. From a single household filter to industrial scale laundry operations, the core technology remains the same. The market opportunity is large. We believe BioShield can make a measurable difference in the quantity of microplastics reaching our waterways, and we are ready to begin.